Good morning, my dear students. Okay, coming to the second module. In first PPT, I explain you about the brief about this what introduction to this module 2. Okay, so in module 2, we are having again the two categories. That is a two title. One is the method of handling boundary condition problem. One more is in that integration part. Okay, so look at here the introduction to stiffness matrix and numerical integrations. Okay, here we are in this module. I already told here we are in the first session. We are going to study about what the shape function and what are the different types of shape function and derivation for all those things. Okay, coming to the second method, that is stiffness matrix. Okay, so here in this video I'm going to tell you about what to mean by stiffness matrix and what are their properties, and as usual we are going to solve some numerical problems based on the method of handling boundary condition. Okay, so look at here. So already I told you in the introduction class about the module 2. This is what the syllabus, whole syllabus. Okay, you are having two subcategory. One is the stiffness matrix method. Okay, that is the method of handling boundary condition and numerical problems, and the different types of shape function which are going to use in the FEM. Okay, so okay, these we have you are having two sub this what these are two title syllabus. Okay, so coming to the stiffness matrix today class, this is very important. Okay, without this we cannot solve the method of handling boundary condition. Okay, normally stiffness nothing but what, it is a force into there is a force divided by deflection. Okay, so that is what the in every FEM problem there will be a what force going to act. Okay, depending upon there we are going to calculate what the displacement, stresses, strain, all those things. Okay, so here the definition stands for stiffness matrix is the stiffness matrix is used to describe the matrix relationship between the force and the displacement. Okay, okay, is called as stiffness matrix. If you consider the temperature problem, okay, that is a thermal problem, then and it is also called as, then we are going to consider the temperature and heat flux. Okay, so such type is called as what, the stiffness matrix. Okay, while coming to the normal bar and beams problem, you are going to correlate with the force and displacement. Okay, and while coming to the thermal problem, you are going to correlate with the temperature and heat flux. Okay, is called as a stiffness matrix. Okay, it is the inherent properties of the structure or beam or given problem. Okay, and it is normally denoted by K. Okay, so in the first class we already derived this equation. Okay, element stiffness matrix. Okay, for a bar element, that is 1D bar element, is given by matrix of Ke is equal to AE by LE 1 minus 1 minus 1 1. Okay, this is the most important formula we are going to use while solving the problems. Okay, without this we cannot solve. Okay, so where A stands for what, area of the bar or area of the given problem, E stands for Young modulus, that is the material constant, and L is the length of an element. Okay, this is the matrix 1 minus 1 minus 1 1. Okay, how we got this equation, already we derived this. Okay, that is by using two methods, that is a minimum potential energy method and one more is a direct method. Okay, so where K stands for stiffness matrix, E stands for number of element which is present in the given element. Okay, so this formula you have to remember. Okay, so coming to the properties. Okay, the second question, this question is also important. They may ask you around 4-mark question. Okay, what is stiffness matrix and what are the properties of stiffness matrix? Okay, look at here, there are 5 properties of the stiffness matrix. Okay, the stiffness matrix is always asymmetric. Okay, consider here one example I shown here. Okay, this is a 3 into 3 matrix. Okay, look at here, stiffness matrix is a symmetric matrix. Okay, so it is always a symmetric matrix. So this is called as a main diagonals are always positive and this is symmetric matrix. Suppose if you fold this matrix in between, okay, all the values should be similar. Okay, this is minus 6 means this is also minus 6, this side also. Okay, this is 0 means this side is also 0, this is minus 1.4 means this also minus 1.4 only. Okay, so it is always symmetric. If you fold this, if you cut the section, all the similar values should be there on the both the side. Okay, so that condition should satisfy that condition should satisfy. That is the first property of the stiffness matrix. Okay, coming to this, stiffness matrix is obtained in the FEA is banded matrix, that is a stored element, it is a banded matrix. Okay, and the main diagonals are always positive. Okay, so look at here, in the main diagonals are always positive. Look at here, these are called as the main diagonals. Okay, so 6, 7.4, 1.4 all always are positive values. Okay, so this is just example. Okay, and while solving the problem, after calculating the global stiffness matrix, you have to check these properties. Okay, if the main diagonals are positive and it is a symmetric matrix means go for applying the boundary condition. If it is not there means again you do the problem, something you did wrong. Okay, so here suppose it is minus 6, so this is 7 means it is wrong, it is wrong. Okay, global stiffness matrix is wrong. Okay, so these two conditions should satisfied. And also third, the main diagonals is always positive. And fourth one is, if the rigid body motion is not prevented, then the stiffness matrix becomes singular. Okay, sufficient boundary condition have to apply to remove the singularity. Okay, and the last one is, if there are n number of nodes, then the global stiffness matrix is n into n matrix, and provide the element for 1D and 2D at each node. Okay, so always it is a 2 into 2 matrix, 3 into 3 matrix, 4 into 4 matrix. It is not a 2 into 4 and 3 into 4, not like that. Okay, so it is always a 4 into 4 and 3 into 3. Okay, so this is about the properties of stiffness matrix and the definition of stiffness matrix. Okay, so this is very important for the point of examination. They may ask you 4 more question. Okay, so what do you mean by stiffness matrix and what are the properties of stiffness matrix? Okay, the stiffness matrix nothing but what? It is a force divided by deflection is called as stiffness matrix, and it is denoted by capital K, and the 1D bar element stiffness matrix formula is given by K is equal to E by L 1 minus 1 minus 1 1. Okay, so here properties is means nothing but what? It is the main diagonals are always positive and it is a symmetric matrix. These conditions should satisfy, and always it is a 4 into 4 matrix, 3 into 3 matrix, 6 into 6 matrix, like that. Okay, so this is about the properties of stiffness matrix. Okay, now coming to the problem section. In module 2 you are having a 5 different types of problem. Okay, so type 1, look at here, type 1 is nothing but constant bar problems, and type 2 is nothing but stepped bar problem, and the type 3 is a tapered bar problem. It is also called as a cross section varying. Okay, and type type 4 is distance gap problem. Type 5 is equal to trusses. Okay, so these are the different types of problems we have to solve in the theory class. Okay, that is what in the theory class. Okay, so if these problems you become perfect, means you can able to get more 20 marks in module 2 subject. Okay, so look at constant bar, nothing but here I shown the images also. Okay, constant bar means the area should be constant. So look at, this is a constant bar section. This type of problem belongs to, we are going to call as type 1 problem, that is constant bar problem. We are going to solve by using elimination method or penalty method. Okay, stepped bar means, look at this diagram shows the stepped bar problem. Okay, so here, so the one element diameter is larger, one more diameter is smaller. Okay, so this type of the problem we are going to call as stepped bar problem. Okay, coming to the tapered bar problem, this is called as a tapered bar problem. Okay, third element, that is the third figure. Okay, taper bar nothing but the cross section of the given bar is varying. Okay, so it goes on decreasing. Okay, such type of problem we are going to call as taper bar problems. Okay, coming to the distance gap problems. Okay, this is one bar element, they will fix some distance. Okay, so this is a bar element, this element is going to fix with help of some element, that external some, they will give some dash. Okay, it is at some distance. Okay, so such type of problem we are going to solve is called as distance gap problem, and this is most important type of problem. Many times they may ask in the examination this question like this only. Okay, and coming to the trusses. Okay, this is a different topic we are going to study. Okay, trusses. Trusses, what is the importance of trusses, we will study in the later class. Okay, and trusses. Okay, suppose if they ask truss problem in, they may give direct 20 mark question only. Okay, so these are the different 5 of different types of problems you are going to solve by using it. There are 2 method of boundary condition, one is elimination method and one more is penalty method. Okay, both the method we are going to solve all these 5 different types of problem. Okay, and you are having a lab. Okay, that is a computer aided modeling analysis lab. These are the part A experiment. Okay, so if you solve these problem in theory class and execute in the software, that is what your part A experiment. Okay, so this is most important. Okay, you have to perfect all these problems. Okay, so just I shown the images. Okay, so many similar type of problem they may appear. Okay, but these different five types of problem we are going to perfect. Okay, so and these method problems we are going to solve by using 2 method, one is elimination method and one more is penalty method. Okay, so in examination they may ask you any one type of method. Okay, if nothing is mentioned means you can solve any one method. Okay, so both, as compared to both, elimination method is very simple. Okay, so just you delete and respect to row and column wherever fixed nodes are there, you are going to get the displacement stress strain. Okay, so these are the method of handling boundary condition. Okay, so what are boundary condition? They are the constraint. Okay, without this we cannot solve anything. Okay, so all those different 5 types of problem we are going to use these 2 method. Okay, elimination method and penalty method. Okay, now we are going to solve by using elimination method. Okay, penalty method we will study in the later class. Okay, what do you mean by the elimination method? So it is a method of handling the boundary condition. In this, wherever the fixed nodes are there, we are going to delete the respective row and column. Okay, that is a known value of. Okay, then we are going to delete the respective node and column. Then we are going to calculate the displacement stress strain. Okay, and in this we are going to calculate the reaction formula is equal to matrix of R is equal to Ku minus F, where K is nothing but what, stiffness, and U is the displacement, nodal displacement, nodal force, F nothing but. Okay, R is the reaction at the support. Okay, so in this I am going to tell us wherever the fixed R node there, that is the known nodes are there, we are going to delete the respective row and column. Okay, so that is what the elimination method. Okay, if you solve one problem means you are going to understand what you mean by exact elimination method. Okay, so now before solving I told every time, okay, the procedure is most important to solve any problem in FEM model. Okay, so the first step of the procedure is what I am going to, all the different types of same procedure we are going to adapt here. Okay, so first you read the problem and identify which type of the problem. Okay, in the examination if you look at the question paper, first you read the problem, so identify which type of the problem in this. Okay, and write the given data and modify that given data. That is, you compare, you have to write all the given data into one unit. Okay, so now you have to analyze, only you have to apply these 6 steps. Okay, first one is construct the FEM model, that is free body diagram. That is, you have to analyze the given diagram as compared to the original diagram, okay, in the question paper. Okay, so you have to remodify that. You have to show the displacement, force, node, length, what are the element which is given, how many element, all those we have to construct the FEM model. Okay, so if you solve one problem means you will understand all these 6 steps. Okay, second is determine the ESM for each element. Okay, so ESM nothing but what? Element stiffness matrix you have to calculate, which is the formula for element stiffness matrix for 1D bar element, that is K is equal to AE by L 1 minus 1 minus 1 1. Okay, coming to the third, that is step 3. So combined, that is determine the global stiffness matrix, and you have to write the nodal displacement and nodal force factor in this. Okay, step number 3, and then write the equilibrium condition. This is the standard equation you have to remember in the step number 4, that is Ku which is equal to F. Okay, then substitute the values and apply the boundary condition. Okay, in the, I told you in the elimination method, penalty method up to step number 4 are same. Okay, while coming to the applying the boundary condition, we have to see the which method they are asking, whether elimination method or penalty method. Okay, elimination method means you are going to delete the respective row and column, and penalty method means you are going to add the maximum C value to the known values. Okay, so you are going to solve in this class only the elimination method problem, so choose elimination method. Okay, so then using the formula, that is you have to calculate the displacement, stress, strain, reaction at the support. Okay, throughout all these different types of FEM model, you need to calculate only these 4 quantities, that is displacement, stress, strain, reaction at the support. Okay, so now before solving, I told you again, the first is you have to remember the procedure, then go for the you have to remember the list of formulas. Okay, then you go for the solution, that is problem solution. Okay, so list of formulas, this before solving the problem we have to remember these formulas. Okay, so first formula is equal to equilibrium equation, that is step number 4. We have to remember this formula, that is KQ which is equal to F. Okay, some book they are denoted as a U, and some book they are denoted as a U for displacement. Q nothing but what? Displacement here. Okay, so then you have to calculate the global stiffness matrix, where K is equal to what? Global stiffness matrix, U nothing but the nodal displacement, and F nothing but the nodal force. So that is a combined forces, all those things. Okay, second one is the stiffness matrix size. Okay, so what is the stiffness matrix size for 1D bar element means, which is equal to the number of nodes and degree of each node. Okay, look at this diagram here, how many nodes are there? 2 nodes are there, so 2 into 2 matrix, like that the stiffness matrix will be there. Okay, coming to the third formula, stiffness matrix for the 1D bar element is, I already told you this, and already we derived this equation, that is Ke is equal to AE by L 1 minus 1 minus 1 1. Okay, step number 4 is what? Stiffness, that is a strain displacement matrix formula you are going to calculate by using this formula, that is B is equal to what? B is equal to 1 by LE minus 1 minus, that is 1. Okay, load vector due to body force is equal to FAE is equal to L by 2 1 into 1. Okay, and load vector due to strain traction force is equal to what? T is equal to T LE by 2 1 1 traction force. Okay, so these are the formula, and the formula for strain is equal to epsilon naught B into U. Okay, B is nothing but what? This, that is the strain displacement here. Okay, and the stress formula in the earlier class, what you studied is strain is what? Stress is equal to strain into Young modulus, but here you are FEM, we are going to use this formula. Okay, that is stress is equal to E by LE minus 1 1, that is here U1 U2, that is the displacement. Okay, Q stands for displacement. Okay, and formula for the reaction to calculate, I already told you in the elimination method, R is equal to K into Q minus F. Okay, these are the 9 formula you have to remember to solve the elimination method or penalty method in FEM, that is type 1, type 2, type 3, type 4, type 5 problem. Okay, so now we are going to move on to the problem section, that is the first type 1 problem. So this is very simple problem. Okay, they may ask you around 8 mark question. Okay, so problem number 1, that is type 1 problem on constant bar, cross section bar. Okay, look at this is the constant bar section, there is no any stepped bar or there is any 3 stepped bar. Okay, nothing. Okay, so since it is belongs to the type 1 number 1, so read the problem carefully. Okay, so problem number 1, below figure shows one dimension, D stands for dimensional. Okay, one dimensional bar subject to an axial loading, taking it as a single element. This is most important, taking it as a single element. Okay, bar element, determine nodal displacement, stress in each element, reaction at the support. Okay, so here I am going to use the elimination method problem. Okay, that is the first method of handling boundary condition. Okay, so first you have to analyze the diagram first. Okay, so since it is only one element is there, they are also mentioned since it is only singular element. Okay, single bar is there. So here in this problem, so Young modulus is given, that is E is equal to 200 gigapascal, and area is given 10 to the power of 4 mm square, and 10 kilonewton axial force is acting at node number 2, and length is given 1000 mm. Okay, so for what is the first step? You have to read the problem. So it is belongs to type 1 and note down the given data. So that is Young modulus for the given bar element E is equal to 200 gigapascal. You have to convert into Newton per mm square, that is 2 into 10 to the power of 5 megapascal or 2 Newton per mm square. Both are units same only. And area of the element 1, since it is only one element is there, so area of element A1 is equal to 10 to the power of 4 mm square. And the length of an element, so since it is only one element, length 1 L1 is equal to 100 mm. And force at node 2, that is a force, this is the node number 1, this is node number 2. Okay, force at 2 node is equal to 10 kilonewton. So here unit, the notation K should be smaller letter, N should be capital letter. Okay, so which is equal to, have to convert into Newton, 10 into 10 to the power of 3 Newton. Just you have to, here I have done mistake. Okay, K should be smaller letter, N should be a capital letter. Okay, so you have to convert. Okay, once you have to convert the given equation, that is given data, into one, it has SI unit. Okay, that is standard equation, Newton per mm square, mm. Okay, once if you calculate all those things, then go for the procedure. Okay, what is the first step of FEM? That is to build a FEM model. Okay, so that is modeling the given bar using single bar element having a 2 nodes. Okay, so since it is a 2 nodes will be there, so write down the free body diagram compared to this. Okay, so look at here, just you draw one bar element. How many nodes are there? 1 and 2. Okay, wherever the this is 1 node, this is 2 node. Okay, so write down here 1, 2, and total length is LE, and this is a force acting at node number 1 is F1, and axially force to F2 is equal to, the given F2 is equal to 10 kilonewton. So just to show F1, F2, and Q1 nothing but what? Displacement at node number 1 and displacement at node number 2. Q2 displacement at node number 2, and L is a length, 2 nodes. Okay, and element number 1 here, this is, since it is only one element, draw only one element. Okay, so this is the FEM model. Okay, that is free body diagram. In this you have to show all the element. Okay, so second step is what? Elements matrix, that is element stiffness matrix. So since it is only one element, you have to use the stiffness matrix for the bar element is given by what? Formula already we derived this. K is equal to AE by L, 1 minus 1 minus 1 1. This is the formula I know. Okay, so since it is in the given problem only one element is there, so for one element, so K1, so put here E stands for element, the 1 is equal to area is given, that is 10 to the power of 4. Young modulus we have 2 into 10 to the power of 5, 1000. Okay, 1 minus 1 minus 1 1. Okay, you have to simplify this, you are going to get 10 to the power of 6 into 2. Okay, then 2 you have to multiply inside, you are going to get 10 to the power of 6, 2 minus 2 minus 2 2. Now this is a what? A stiffness matrix. Since it is only 2 element is there, 2 into 2 matrix, you have to write here 1 2 1 2. Okay, so what is the property of the stiffness matrix? The main diagonals are always positive. Yes, it is always positive, we got the positive values, and it is a symmetry. If you fold this, minus 2 minus 2. Okay, so since the condition is satisfied, then go for the next, that is a global stiffness matrix. Okay, in global stiffness matrix, since only one element is there, okay, so same as it is, that is K1 is equal to K, that is 10 to the power of 6, 2 minus 2 minus 2 2. Okay, so here then next, what is the nodal displacement factor? Okay, here only 2 is there, so Q is equal to Q1 Q2. Okay, so these are the displacement. Okay, and load vector, that is F is equal to F1 F2. Okay, so F1 is it is here, the fix is there, so there is a no moment, so put up take value F1 is equal to 0, and F2 they given 10 kilonewton into, which is equal to 10 into 10 to the power of 3. Okay, so now go for step number 4, equilibrium condition. Okay, the equilibrium condition for the bar is given by KQ, which is equal to FQ, nothing but what? The displacement. Okay, K already we calculated, that is a global stiffness matrix, substitute all the values, Q value and F value. Okay, so here node number 1 2 1 2. Okay, so now what is the condition here is, since node number 1 is fixed, okay, known values you know here, displacement also 0 and force also 0. Okay, so here according to the elimination method, so you have to delete. Okay, so next apply the boundary condition. So from the figure 1, so that is what, Q1 is equal to 0 and F1 is equal to 0. By using the elimination method, we have to delete the first row and first column, that is here, this you have to delete this first row first column, first row first column, first row first column. Why we want to delete? Because node number 1 is fixed, there is a no moment, so remaining is only the 10 to the power of 6, that is 2 Q2 10 to the power of into 10 to the power of 3. Okay, that you have to write here, 2 into 10 to the power of 6, this 2 into 10 to the power of 6. Okay, Q2 which is equal to 10 into 10 to the power of 3, and Q2 is equal to 0.005 mm. Okay, so this is the displacement at node number 2. So now the nodal displacement are what? Q is equal to Q1 Q2, Q1 is equal to 0, Q2 is equal to 0.05 mm. Okay, so this we got the displacement. Okay, I hope you understand this step is very important to delete the elimination, that is what, first row first column, because of known fixed values. Okay, so once if you know the nodal displacement, then go for the strain in each element. We listed out the formula. Stress in each element is equal to what? Stress is equal to Young young modulus by LE minus 1 1 q1 q2, that is u1 u2, that is this is the displacement. Okay, already we calculated the displacement value here. Substitute here, you are going to get stress in each element is equal to minus 1 1 0. You have to substitute, you are going to get 1 megapascal. Okay, stress is equal to 1 megapascal or Newton per mm square. We calculated the stresses. Okay, then finally coming to the third, that is the reaction at each support. What is the reaction at each support? Formula we have, that is R is equal to K1Q minus F. Okay, already you know the K value, substitute here. U value already you calculated, 0 minus 0.05, and F already they given. So here how many nodes are there? 1, 2, R1 and R2. Okay, you simplify this, you are going to get R1 is equal to minus 10 into 10 to the power of 3, R2 is equal to 0. Okay, so this is about the reaction. Okay, like this you have to solve the elimination method problem. Okay, this is what the method of elimination method problem. Okay, 1D bar element. Okay, so this is like what to solve the problems on 1D bar element. Okay, same problem we are going to solve by using a step bar and what 3 element noded element and distance gap problem. Okay, so the main thing is how to delete the first, that is how to delete the known values, that is most important, and simplification. Okay, so this is about the problems on elimination method of single bar, that is a type 1 problem. Okay, so I hope you understand this problem. Okay, so in coming class we are moving to the second different types of problem. Okay, I hope you understand this. Okay, thank you very much.